f of x. Say it looks something like this. Say you also want to find the slope at this value. Or in other words, the tangent line at, let's say this is at 3. Basically, you want to find the tangent line at x equals 3, which is another way of saying that you want to find the slope of this imaginary line at x equals 3. But how would we find this? Because often we were told in math that you need more than one point to approximate um, the value for a specific slope. One way we can use one thing we could use in finding this tangent line is using secant lines. Basically using secant lines, we're basically trying to find the closest approximation to this line. So we want to have our second point as close to the first one as possible. So basically, this is where limits come in, because we are constantly getting our second point closer and closer. It like leans towards the value at this x value. So basically we'll say say x is equal to 1 and then x is equal to 2, 2.5, and then say 2.9. This is basically representing our secant line, right? As x approaches 3, our f of x is basically gonna go to a specific number, let's say 12. And how we would express this is basically saying the limit of f of x as x approaches 3 is going to be equal to 12. And this is how we can use limits and secant lines in order to find the line tangent to the function at a given point. Do anything else? Let's truly get into what a limit is. So basically what this is saying, all of this is basically saying as x approaches the value n, let's say value n, what is the limit f of x approaches? This is basically what all of this is saying. So when we have graphs that look something like this, where it's obviously leading to a point, and maybe it's discontinuous at other points, we can, this helps us to get the value at say, a specific value, n. So let's say n is 2. This would just be represented as lim as x approaches 2 of f of x. And we could see using this graph that as it approaches from either side, whether it's from the left or from the right, it approaches this value right here or at 3. So we would just say this would be equal to 3 because from the left and the right it approaches the value of 3. Now if you wanted to represent as like specifically which direction it's coming from, as like x approaches 2 from the left side, this is going to be represented by negative. So negative for left side and positive for right side. And what I mean by this is that if you want to include which side it's coming from, then you put an x or a plus right here. So this shows us what limits are in its I guess in simple terms. And as we've said before, this would be represented by God. The table would basically look like x f of x as it approaches 2, the values come closer and closer to 3. So it could be 1.9 right here or 1.75, and it's going to be a value that's close, like that's approaching 3. So 2.6, 2.7. So that's basically how you would represent it in these terms as well. Now let's work on how we would actually solve a few limit problems. So how we would solve something like this is a very basic function. How we would solve this is by substituting 1 for x. So since we don't have to factor out anything or move anything around, it's just going to be the same value regardless of how we change it. So this is just going to be equal to 1 squared or 1. But once we start to get a little bit more complicated, say as x approaches 1, x squared minus 1 over x minus 1. If we were to just plug in 1 on its own, then we would get a undefined number. We get 0 over 0, or we get undefined. So in order to avoid just getting a 0 flat out or an undefined, we could substitute, or not substitute, but we can move around this this function in general in order to, I guess, change it and factor it out to, I guess, like to a state where we could like substitute x for 1 and have it not equal to 0 or be undefined. So it's not guaranteed that it will 100% like, I guess, like work. Like it won't guaranteed, it's not guaranteed like if you factor out everything for it not to be equal to 0. It might still equal to 0 or be undefined. And this is just like extra, I guess, extra things that we're doing to make sure that it's, I guess, 0 or not 0. So we want to change this into x plus 1 times x minus 1, because since we're factoring, we want to be able to get rid of this. because 1 minus 1 is going to always equal to 0. So this just turns into x plus 1 times x minus 1 divided by x minus 1. And we can factor out x minus 1 and use x plus 1 and to substitute 1 for x. So this is going to be equal to 2. So we're going to see a lot of limit problems looking like this. They're going to be fractions containing numerators that could be like looked at as functions, and denominators that could also be looked at as possible separate functions. If, like, for example, it might look something like, I don't know, x squared plus 3x minus 5 over x plus 1, for example. It could look something like this. So practicing with, more complex, this is a very basic version of it, but it shows us why just putting in 1 for x isn't always the desirable thing to do, because then we're not going to be able to find um, its actual like number. Look at a practice problem we could do. X approaches 2. Alright, so try and do this yourself if you can. Pause the video and try to do the following limit and come back and we can compare answers. Alright, so as we've said before a few seconds ago, we can't just simply plug in x for 2, because 2 to the second minus 2 times 2, it's literally just going to be 4 minus 4. So what we're going to do is we're going to break apart the numerator and the denominator. So the numerator, we'll be working on this right now. X squared plus 4x minus 12. See here, you multiply the ends. Let's just do it from here. So it's going to be negative 12x if you, or x to the second if you multiply them together. And I think it's 6x and negative 2x. So then it's just going to be x to the second plus 6x minus 2x minus 12. We could turn this into x plus 6, negative 2, x plus 6. This turns into x minus 2 times x plus 6. This is what the numerator is going to be. And now that we found the numerator, we can find the denominator. Let's erase this first. Alright, we know that this is the numerator. So for our denominator, x squared minus 2x, we could just take out an x minus 2. And so it's literally just going to be x minus 2 times x plus 6 times, or divided by x times x minus 2. And now that we've taken this apart, we've broken this apart, the numerator and the denominator, we could get rid of x minus 2. So then what we're left with is x plus 6 divided by x. And now we could plug in for 2, and that's just going to be equal to 8 over 2, which is equal to 4 right here. So basically what this means is the limit as x approaches 2 of this function is going to be equal to 4. And let's take a look at its or this function's graph. So this is the function that we were just talking about just a second ago. X squared plus 4x minus 12 divided by x squared minus 2x. This is the graph. And we see at x equals 2, it's going to be undefined. So how are we able to find a solid number for the limit problem? Well, basically, what that question was asking, the limit as x approaches 2, it wasn't asking, oh, what is the value that it becomes as x approaches 2, but rather, what does it approach? So as x approaches 2, what is the value, or what is the value that it comes closest towards, or what is the value that it approaches? And as we can see right here, despite it being undefined, we can clearly state that it's 4, right? Because, we see it right there. It's easy to graph. It could be considered, it is considered undefined, but with limits, the neat thing about that is that it helps us to find the value that the function approaches as x approaches 2. So this is going to be very vital for calculus because we're going to need to find values that might be undefined regularly. Using just like regular functions and graphing, we might find that, oh, it's undefined at this point. And the neat thing is that we could use limits in order to find what is the value that it's approaching. So that could help us out um, in a variety, like in a bunch of different ways. Uh, like as we continue this calculus course, uh, it'll start to make more sense because we're gonna be uh, basically using values that may not like exist regularly with the function, but we're gonna have to use stuff like limits and derivatives um, in order to find what is the value that it approaches as x approaches like a given point. Let's take a look at a special case right here. So this function is basically going to be basically a step function where it's saying the limit of f of x as x approaches 0. F of x is equal to 0 if x is less than 0, and 1, or f of x is equal to 1 if x is greater than or equal to 0. And we see right here we're given the graph. As x approaches 0, it not only from the left hand side it approaches 0, and from the right hand side it approaches 1. So regularly, like if it was plus or minus basically meaning from the left hand side, plus meaning from the right hand side, we could easily say, oh, from the right hand side it as x approaches 0, from the right hand side y is going to be equal to 1, and from the left hand side it approaches 0. We could see that right here from these arrows. But in this case, we're just told the limit of f of x as x approaches 0 in general. So since this is a step function, we can't specifically say where it approaches as x approaches 0. So we would just say that there is no limit for this. But if it was, say, like, as x approaches 0 from the right hand side, that would be equal to 1 easily. But since we don't have one limit it approaches towards, and it's not asking from the left hand or right hand side specifically, then we are just to say that this does not exist, or the limit does not exist for this step function. So now that we've gone over limits, let's go over rate of change. So what is a rate? Let me rewrite that actually. So what exactly is rate of change? So when I say this out loud, rate of change, immediately you think of, oh, this basically means the rate at which something is changing. So the point of rate of change is basically to determine how fast f of x is changing at x equal a. This could be any value, like x equals 4, x equals 5, just like with the limit problems. So there are two, I mean there's rate of change and there's also instantaneous rate of change. At x equals a. So basically what we're going to be going over today is more instantaneous rate of change. It's practically the same, but in order to determine, let me erase this. But in order to determine instantaneous rate of change, we must follow a specific formula that we're actually going to be using quite a bit in calculus in general. So instantaneous rate of change is basically going to be equal to f of x minus f of a divided by x minus a. So we're basically saying the change in f of x divided by change in x. And this will help us to find the instantaneous rate of change for us. Or how fast f of x is changing at x equals a. So let's take a look at a practice problem. Just want to make sure I'm writing this correctly. So basically the air in a balloon is represented by this function right here. And basically finding the instantaneous, or basically what we're gonna be doing is finding the instantaneous rate of change of the volume of a balloon after t hours. And basically we're gonna be just saying like t equals a. So we're literally just gonna be saying v of t minus, in this case we're going to be trying to find the volume of this balloon after 5 hours. So it's going to be v of t minus v of 5 divided by t minus 5. So this is how it would be represented if we're trying to find after 5 hours. All we would really have to do is just write out the function. So it would basically look like, let's see here, t to the third minus 6t to the second plus 35 minus 10. Because if you were to plug in t for 5, then it would be equal to 10. Divide this by t minus 5. That's what it would turn into. Then, we could get rid of this, obviously. That's a very small brush. So we'd be basically left with this. And we've seen these kind of problems before. We were talking about, whoops. We're basically talking about with the limit problems. This is essentially what we were dealing with before. And we would basically use the same thing. Um, we would just take out the numerator and pick it apart. And eventually we would end up with t 15. This would be our instantaneous rate of change if we followed if we picked apart the numerator and denominator and were able to divide out, be equal to 15. So basically what this is saying is the rate at which this function is changing, or the rate at which the volume of the balloon is changing after 5 hours, is going to be 15 centimeters cubed per hour. Because with this specifically, like, velocity is taken into account, so it's gonna be represented by this. So with like certain problems like this, where it's practically like word problems and it's asking you what the velocity of something is gonna be, or uh the rate at which something is changing, or say like the rate at which like a car is like speeding up, like on the road. Ugh, this is awful drawing. We're basically trying to find out, like, at which, like, how fast is it changing at a given amount of time, or at once, which we're gonna get into later on. But if we were, like, say if we were to plug in 4, if it was after 4 hours instead of 5, then it would be 0. We'd end up with 0 in the end. And this isn't to say that it's not going to move, or it's not going to I guess this isn't to say that like it's just completely stationary. This just means that at like 4 hours it's not going to change. So this practically means that it is not changing at all. And if it's a negative number, say like negative 10, centimeters cubed per hour, then that basically means that it is shrinking. So negative is basically shrinking, positive is increasing, and zero is stationary. All right, so one final thing before we finish up is we're just gonna go over a bit of what we were just talking about. So if you noticed, even with like the slope at the tangent line, it all boils down to one e equation, which is f of x minus f of a divided by x minus a. This tells us the slope of the tangent line, rate of change, instantaneous rate of change, and it can also help us to solve word problems. Just this equation right here. So when we're asked about rate of change or tangent line, and it boils down to this fraction, we're pretty much being asked the same question. Um, in order to find the average rate of change of f of x over the interval of x as x approaches x plus h, because before when we were talking about how the last problem, when we changed t from 5 to 4, it went from like a solid number to just 0. So that small little difference changed the output by a great amount. We could basically just say f of x was changed to f of x plus h, for example. We could say like negative or whatever the hell. Basically, a better way, because we could, if f of x has like small changes, what if we want to understand how f of x changes if we just do little small tweaks to it? Because just because we decreased our t to oops, sorry, just because we increased or like decreased our t from like 5 to 4 or 4 to 5, or we change it by 1, or we change x to um I don't know, like we add 1 or we decrease 1, since it changes in a like a very like I guess substantial way, we're going to uh go over another basically a better way of finding the rate of change, and like how how much like f of x changes with small changes done to it. So this is going to be represented like a better way of doing this. Oops, keep doing that. I'm going to write this down. So this right here is basically helping us to or helping to show us how much f of x changes as it's added like with small variations to it, which is going to be h. And so this is a very important a fraction for us in calculus, because we are going to be using this to find the derivatives of certain functions. We're going to be, I don't know if we could say div. It's derivative, you know what I'm saying? We can find derivatives. We could find rate of changes, and we can use this formula right here to find derivatives, rate of change, and a bunch of different other stuff in the future chapters of Calculus 1 with this equation right here. So This is just going to be a notation formula that we're going to be using in the future. But this is going to basically help us to find how f of x changes as it is increased, as it increases. So this is going to help us to find instantaneous rate of change in a more efficient way. And that is going to conclude this video for limits and rates of change. And check out my practice videos just so I know I'm not really amazing at it explaining the logic behind this, but the key point is to understand what equations we have to use and why we're using like why is this h here, you know, or uh what the like tangent line tells us about a function or what the rate of change tells us about a function. So I already have a video up regarding like limit practice problems, but soon we're gonna get into more problems that revolve around I guess uh you know, the usage of notation formulas like this one right here. But one thing's for sure, this is definitely going to be a vital part of future calculus chapters. And yeah,